Okay, so the next question that we have here is question number 13, which asks, show that the relation R, so that is exercise 13, and the question is, show that the relation R, the relation R in the set of all in the set A of all polygons as, so basically A is the set of all polygons as R is equal to basically all the ordered pairs P1 comma P2, such that P1 and P2 have the same number of sites. P1 and P2 have the same number of sites. So this is the relation that we have, is an equivalence relation. And also, what is the set of all elements in A? What is the set of all elements in A related to the right angle triangle T, related to the right triangle T with sides 3, 4, and 5. Okay, so the question is, show that the relation R in the set A of all polygons as R is equal to basically all the ordered pairs P1 comma P2, such that P1 and P2 have the same number of sites, right? And you want to show that this relation is an equivalence relation. And then the second part of the question we will answer once we have done the first part of the question. So let's see why we can solve this problem. Okay, so first of all, what you want to do here is basically you want to show that this relation is an equivalence relation, meaning that you want to show that the relation is reflexive, symmetric, and transitive, right? So to show that the relation is reflexive, what you need to do is that basically that condition is that A comma A belongs to R for all A belonging to A, right? So what that means is that of course basically A and A comma A does belong to R for all A belonging to A, meaning that, well, if you imagine that there is some P1, for example, belonging to A, then of course, meaning that if basically there is P1 belonging to A, then P1 comma P1 does belong to R for all basically P1 belonging to A, because basically P1 always has always has the same number of sites, has the same number of sites as P1, right? So P1, the number of sites of P1 is of course equal to the number of sides of P1. So P1 comma P1 always belongs to R, which means that basically R is reflexive, right? So that is the first part. The second part, you want to show that R is symmetric. You want to show that R is symmetric. So how do you do that? So basically the condition for being symmetric is if basically, for example, A1 comma A2 belongs to R, then that implies that A2 comma A1 also belongs to R for all A1 and A2 belonging to A, right? That is the condition. Meaning that suppose that for example some A1 comma A2 does belong to R. That implies that A1 is a polygon having the same number of sides as A2, right? And well, if A1 is a polygon that has the same number of sides as A2, then that implies that A2 is also a polygon having the same number of sides as A1, right? So which implies that basically A2 comma A1 does belong to R as well. So basically, since A1 comma A2 belongs to R and also A2 comma A1 belongs to R, then based on this condition that we said, that we wrote here, that means that basically R is symmetric. Now we want to show that basically R is transitive. And as there was something like an expression in one of the movies of Tom Hanks. I don't remember the name of the movie, but there was a guy in that movie that used to say they were digging some hole in a wall in order to basically get into some casino and rob the casino of all the money that there was in the casino and so on. Basically, they were doing this tunnel under the wall in order to get access to the main safe in the casino. And there was a guy in that movie that was in charge of basically all of those tools and basically digging and everything. Every time he used to say he didn't really care about what was being asked of him. Every time he used to say, easiest thing in the world. So I was reminded of that part of that movie, which was pretty funny actually, if you have seen the movie. Now, so you want to show that R is transitive. Well, that's again easiest thing in the world. So in order to show that R is transitive, you want to show that basically if A1, for example, if A1 comma A2 and A2 comma A3 both belong to R, that implies that A1 comma A3 A1 comma A3 belongs to R as well for all A1, A2 and A3 belonging to A. So now let's see if that's the case, or that can be done here, meaning that you have basically, let's assume that A1 comma A3 and A1 comma A2 and A2 comma A3 both belong to R. That implies that basically A1 is a polygon having the same number of sides as A2, and this part means that A2 is a polygon having the same number of sides as A3. So since both A1, A2 and A3 have the same number of sides, then you can say that A1 is a polygon having the same number of sides as A3, which means that basically A1 comma A3 does belong to R. Now over here we are assuming that A1 comma A2 and A2 comma A3 belong to R, and we have concluded that A1 comma A3 does belong to R as well, which means that R is transitive. R is transitive, right? So the first part of the question is answered, and well, of course, R is reflexive, transitive, and symmetric, which means that R is an equivalence relation. That's the first part of the question. The second part of the question is, what is the set of all elements in A related to the right triangle T with sides 3, 4 and 5. Okay, so now you see over here we are talking about a right triangle, and here we are talking about basically A is basically the set of all polygons, right? A polygon by definition is basically a polygon, meaning that by definition a polygon is a closed geometric shape, simple geometric shape, is a closed, simple, and all of these words are important. Closed, simple, basically 2D geometric shape made up of straight line segments. So what that means is that, first of all, if a geometric shape is closed, it's basically something like this. For example, if you have this geometric shape, this is not closed, because you have these two vertices that they are open. This kind of situation is called not closed. So this is open. If you have this geometric shape, on the other hand, this is a closed geometric shape. Now, a geometric shape can be can be simple or not simple, meaning that, for example, this geometric shape is not simple. You see that there is an intersection of these two sides. So this point of intersection means that this is not simple. On the other hand, this geometric shape is simple, because none of the sides have basically no two sides have a point of intersection. So that's a simple geometric shape. That's a not simple geometric shape. And of course, you know what the geometric shape is, that all of these are, well, called geometric shapes, two-dimensional geometric shapes. And 2D means that you can fit that geometric shape on a piece of paper. Suppose that you have a piece of paper, sheet of paper. You can put that sheet of paper on your desktop, and on the top of the desk, it's two-dimensional, meaning that what you can do on that sheet of paper, suppose that this is the sheet of paper, what you can do with that is that you can either go in this direction or you can go in this direction, meaning that this is y and this is x. But the sheet of paper doesn't have any depth to it, meaning that you cannot draw a line into the sheet of paper. If you push your pen hard, the sheet of paper you're going to make a hole in the sheet of paper. So you cannot draw a line in that direction, meaning that you cannot go inside, right? Which means that it's a two-dimensional sheet of paper, and a two-dimensional, basically on such a basically sheet of paper, you can draw all kinds of two-dimensional geometric shapes. For example, a triangle, or a pentagon, or a square, or a trapezoid, or basically a rectangle, or things like that. But this kind of thing over here, this is a cuboid, right? So a cuboid, you cannot draw it on a you cannot draw a cuboid on a sheet of paper, although we usually do this kind of thing on a sheet of paper. But since this is a cuboid, and this is actually a 3D shape, and of course all the dimensions cannot be shown on a sheet of paper. You have to use some sort of perspective or point of view in order to look at the cuboid in 3D space, and then somehow manage to draw whatever we see of the cuboid on a 2D sheet of paper, right? So that's basically, that is called a three-dimensional shape, meaning that you have this dimension, and you also have this dimension, and you also have this dimension. So this dimension over here, this doesn't fit on a sheet of paper, meaning that on a sheet of paper you cannot tell how deep this cuboid is. It's not possible to tell unless they give you the dimensions, right? So what that means is that basically it's a closed, simple 2D geometric shape made up of straight line segments. These are all straight line segments. But if it's not a straight line segment, then it has to be a curve, meaning that, for example, you would end up with something like this, or you would end up with something like this. These are curves. These are no line segments, no straight line segments. So a polygon cannot be made of curves. It has to be made up of straight line segments, right? So with that definition, what that means is that then a polygon it has to be closed, it has to be simple, meaning that this kind of thing, this intersection is not allowed, and it has to be made up of straight line segments. Now it turns out that the simplest polygon in terms of the number of sides that you could have is basically a triangle. So a triangle is basically a polygon having 3 sides, 1, 2, and 3. This is a triangle, and this is a type of a polygon. Then you, after a triangle, you could have, for example, a square. A square is a polygon having 4 sides. And that's again a type of a polygon. Then you have, for example, the idea of a rectangle. That is again a type of a polygon having 4 sides. But of course you can argue that, for example, you can argue that basically the square is just a special case of a rectangle, or the other way around. I don't remember exactly, but you can treat these two as the same type of polygon, because both have the same number of sides. And then you have the idea of a pentagon, meaning that you have 5 sides over here. So 1, 2, 3, 4, 5. So 1, 2, 3, 4, and 5. This is a 5-sided polygon. This is a 5-sided polygon called a pentagon. And you can just keep going, like for example for hexagon, 6 sides, heptagon, 7 sides, octagon, 8 sides, nonagon, 9 sides, and then there is 10 sides as well, which I don't really know what they call it. So that's a polygon. That means that the polygon, when what we say here is that we are concerned about basically the set of all polygons. It doesn't really matter. The side length doesn't really matter here, right? So the only thing that matters here, that as far as the relation is concerned, is basically P1 and P2 have the same number of sides, right? And then what we are asking here is, what is the set of all elements in A, the set of all elements in A related to the right triangle T with sides 3, 4, and 5. So as you can imagine, then the only thing that is important here really, as far as specifying which basically what set of polygons are related to this triangle in set A, is that basically what's important here is that to understand that the right part is not important, because it could be any type of triangle, and as long as it has the same number of sides as the other, basically as P1 for example, or as P2, we are good to go. We are not concerned about whether the triangle is a right triangle or a non-right triangle, right? So important is that it's a triangle T, and the side lengths are just simply not important, because it could be any side length. The number of the sides is actually important. So that means that basically, now the question is, what is the set of all elements in A related to a triangle, just simply a triangle, right? And since basically all triangles in this set, all triangles in set A are related to this triangle by this rule, then you can say that the set of all elements in A, you can say that basically the set of all elements in A related to triangle T is the set of all triangles in set A. Meaning that any triangle that you can find in set A, it's going to have 3 sides. It doesn't matter what side length they have, or it doesn't matter whether it's a right triangle or an acute triangle or an obtuse triangle or whatever that might be. It doesn't really matter. All that matters is that the triangle has 3 sides, and since it has 3 sides, basically based on the rule that we have, it's going to be related to the other element in the set, and so they are related. So then you can say that the set of all elements in A related to triangle T, this is not delta T, but this is triangle T, is the set of all triangles in the set A. So let me take a look at the solution here. As the set of all elements in A related to triangle T is the set of all triangles. That's exactly correct. Okay, so the next question that we have is question number 14. Let's see what. Okay, so question number 14 is, let L be the set of all lines in XY plane. So this is exercise 14. Let L be the set of all lines, the set of all lines in XY plane, and R be the relation in L defined as R is equal to basically all the ordered pairs L1, L2, such that L1 is parallel to L2. So L1 is parallel to L2. Show that R is an equivalence relation. We want to show that R is an equivalence relation, and also find the set of all lines. Find the set of all lines related to the line y is equal to 2x plus 4. Okay, so that's the question. Now, in order to answer this question, first of all, L is the set of all lines in XY plane. So L is the set of all lines in the XY plane. And R is the relation in L, defined as basically R is equal to all the order pairs L1, L2, such that L1 is parallel to L2. And you want to show that R is an equivalence relation. Basically, to show that R is an equivalence relation, you need to show that R is, first of all, reflexive. Now, to show that R is reflexive, basically reflexive means that A, A belongs to R for all A belonging to A. That's the condition. Now, of course, you know that every line is parallel to itself. So you can say that since every line is parallel to itself, therefore basically L1 comma L1 belongs to R. Or you can say that basically A comma A belongs to R for all A belonging to A, and therefore R is reflexive. Therefore R is reflexive. Now, in order to show that R is symmetric, what you need to do is that the condition is that basically if A1 comma A2 belongs to R, that implies that A2 comma A1 also belongs to R for all A1 and A2 for all A1 and A2 belonging to A, right? So let's suppose that, assuming that A1 comma A2 belongs to R, that implies that basically A1 is a line parallel to L2, to A2, I'm sorry. Therefore, you can say that A2 is also parallel to A1. A2 is also parallel to A1, which means that A2 comma A1 also belongs to R, which means that basically R is symmetric. R is symmetric. Now, in order to show that R is transitive, basically you want to show that if A1 comma A2 and A2 comma A3 both belong to R, then that implies that basically A1 comma A3 belongs to R for all A1, A2 and A3 belonging to A, right? So now let's assume that basically A1 comma A2 belong to R, and also A2 comma A3 also belongs to R. So that implies that basically A1 is a line parallel to A2 and A2 is a line parallel to A3, which means that basically A1 is a line parallel to A3. A1 is a line parallel to A3, which means that basically A1 comma A3 also belongs to R, right? Which means that basically here we are assuming that A1 comma A2 belongs to R, A2 comma A3 belongs to R, so A1 comma A2 belongs to R, A2 comma A3 belongs to R, and also A1 comma A3 belongs to R, which means that basically R is transitive. Now, we basically we showed that R was reflexive, symmetric, and transitive. So that means that R is an equivalence relation. Equivalence relation, right? So R is an equivalence relation. Now what that means is that, so basically the first part, R is an equivalence relation. We have already shown that. Now you want to find the set of all lines related to the line y is equal to 2x plus 4. The set of all lines related to y is equal to 2x plus 4. So you see that basically you see that if two lines are basically, if I think of basically a straight line as y is equal to mx plus c, m is basically the slope of the line and c is the y-intercept of the line. The y-intercept is basically the point through which the line goes through the y-axis. Meaning that, for example, this line over here, in the case of this line, y is equal to 2x plus 4, basically 1, 2, 3, and 4, this is one point on the line, in basically where the line goes through the y-axis, and also the slope is 2. Meaning that for 1 unit of horizontal change, you have 2 units of vertical change, meaning that you would end up, this would be another point on the line, and then this would be the graph of the line, right? So basically this 2, or the slope of the line, or basically this 2, or m over here, which is the slope of the line, well, it basically tells you what the slope of the line is, meaning that how steep the line is. And also c tells you what is the y-intercept of the line, meaning at what point the line goes through the y-axis. So now, in order for two lines to be parallel, of course the slopes have to be the same, meaning that if I have another line over here, so for example y is equal to 2x plus 5, then I would have this line over here exactly parallel to this line, but going through this point, which is equal to y is equal to 5. But having the same slope, and so they are parallel, right? So that means that basically means that if two lines are supposed to be, you can say that if the line L1 is parallel to the line L2, then basically M1 is equal to M2, right? And vice versa, of course. Meaning that the converse of this is also true, meaning that if M1 is equal to M2, then L1 is going to be parallel to L2. So now the set of all lines related to this line in the xy plane is going to be basically all the lines having the same slope but not having the same y-intercept, because if they have the same y-intercept and if they have the same slope, then you would end up with the same lines, which is, so since we are talking about different lines, so the lines are supposed to have the same slope but different y-intercept, meaning that the line is supposed to be all the lines going in this direction and all the lines going in this direction, but not the line itself. If you basically tried the same y-intercept, of course you will end up with the same line having the same slope here. So what that means is that then you need to basically find, since you want a set of all lines related to this line, so of course the line has to be based on this definition here. The lines have to be parallel to be related. So since the lines have to be parallel, and so basically the lines have to be parallel. So let me write it this way so that we break that down. So we can say that the lines have to be parallel, right? Which implies that basically the M1, for example, is equal to M2. Now you can take M1 for the you can say that, for example, if I call this for example M, then M has to be equal to M of I, for example, and M of I denotes all the slopes of all of those parallel lines parallel to this line, right? And the lines have to be different lines other than y is equal to 2x plus 4, which implies that basically the y-intercepts, the y-intercept of the lines is not supposed to be 4. Other than 4, any other number is acceptable. 4 is not acceptable, because otherwise you would end up with the same line. So that means that now basically an equation that describes basically this line is that y is equal to basically 2x, so the slopes have to be the same, plus some c, where c is not equal to 4, right? So that is basically the set of all lines related to this line under this relation R, right? So the line parallel to the given line of the form y is equal to 2x plus c, where c belongs to R. Hence the set of all lines related to the given line is given by y is equal to 2x plus c, where c is, well, of course they have argued here that the line, that basically this line itself is of course parallel to itself. So you can take out this exclusion that I have made here, meaning that I have made it a condition here that says that the lines have to be different lines other than this line, but it can be that line itself, because that line is of course parallel to itself, which means that what I said was actually not entirely correct. So you can say that then y is equal to 2x plus c, and then you can say that where c, basically you can say that where C belongs to the set of real numbers, right? So this solution is of course is correct. What I said was not entirely correct. I apologize for that. Okay, so but well, I would take this part out, and I would redo this part of the part that is related to basically the line, the last part. But since there was a couple of things that we talked about the lines, I'll just let them be there. And although what I said was not actually correct, but then you will learn a couple of things about lines and the y-intercept and so on and so forth. So I'm not going to erase that. So in the next video we will talk about exercise number 15 and 16. I'll see you in the next video.